welcome to the deep dive. This is where we take topics you're curious about, look at the source materials you send us, and really pull out the essentials, the fascinating core stuff.
Yeah, no wading through jargon. Just the aha moments.
Exactly. And today, we're focusing our metaphorical telescopes, let's say, on our closest cosmic neighbors, the stars right around us. This deep dive comes from a scientific paper you shared, looking at these nearby stars and, critically, the impact of the Gaia space mission, which sounds pretty big.
Oh, it is. Think of this as like your fast track to understanding a really complex area. Our mission, if you will, is to give you a clear, engaging picture of what we know about the stars closest to our sun.
Okay.
We'll look at how astronomers tried to map this area before, the real challenges they bumped up against.
Right.
And then how Gaia just completely rewrote the rule book. It's like getting a backstage pass to our solar system's immediate neighborhood.
Okay, love that analogy.
Yeah.
Let's start with basics. Nearby. That feels, well, relative in space, doesn't it?
It absolutely is. That's a crucial first point.
So when astronomers talk about nearby, what sort of distances are we actually dealing with?
Good question. Usually nearby means within, say, 10, 20, maybe up to 50 parsecs from our sun.
And a parsec is, remind me.
About 3.26 light years. Now, to give that some scale, think about the sun's distance from the center of the Milky Way. That's around 8,000 parsecs.
Wow, okay, so 10, 20, even 50 parsecs is really just our immediate doorstep, cosmically speaking.
Exactly. We're zooming way, way in on a very small local bubble within our galactic disk. It's dominated by the stars closest to us.
Right, just a tiny corner.
Yeah.
But why put so much effort into studying this, well, relatively small patch?
Because this local region is fundamentally important. It's where we get the baseline data for understanding, well, so much about the Milky Way itself.
Like what specifically?
Things like the stellar luminosity distribution, basically. You know, how common different types of stars are brightness-wise.
Right.
We can estimate the local mass density. Figuring out how much stuff, stars, and potentially unseen matter is packed into this area. We study how these stars are moving, their velocity distribution, which tells us about the dynamics right here. And of course, it's the prime hunting ground for discovering and really studying things like binary stars, brown dwarfs, white dwarfs, even exoplanets orbiting these stars.
And the key is that because they're closer, we can measure them better.
Precisely. The closer they are, the more accurate our measurements can be. Better data, better understanding, it all starts here.
It makes total sense, like studying your own town to understand the whole country. Now, the paper mentions that just counting these neighbors has been, well, a big challenge. Why so hard to get a complete census, even of the really close ones?
Yeah, it's surprising, isn't it? Even within, say, 10 or 20 parsecs, getting a truly complete list has been incredibly difficult for a long time.
Why is that?
Well, back in the early 20th century, astronomers relied heavily on ground-based parallax measurements. You know, watching how a star appears to shift against the background as Earth orbits the sun.
Right, triangulation.
Exactly. And that worked pretty well for the brighter nearby stars. But the problem was, and still is to some extent, the faint stuff.
The dim ones.
Yeah, low luminosity stars like low mass M dwarfs, and especially those weird objects called brown dwarfs, sort of failed stars, they're just incredibly hard to see. So for ages, a full count of everything in that 10-20 parsec range was just out of reach.
So faintness is a big part of it.
Yeah.
But the paper also talks about surveys in the 70s and 80s looking for stars with high proper motion. What was that about?
Right, proper motion. That's a star's apparent movement across the sky over time. The idea was nearby stars should appear to move faster against the distant background.
Like watching closer trees whiz by faster than distant mountains when you're driving?
Perfect analogy. So these surveys looked for stars zipping across the sky, hoping they were nearby. And they did find some candidates that were then checked for parallax.
Was a but, I sense.
Well, yeah. It turned out these surveys had a bit of a bias. They tended to pick up high-velocity halo objects more often.
Halo object.
Stars that aren't part of the main flat rotating disk of the galaxy like our sun. They're on these weird, elongated, tilted orbits, kind of just passing through our neighborhood. Cosmic tourists, if you like.
Ah, okay. So they were catching some unusual passersby. So before we had these like massive all-sky surveys, what else did astronomers use?
They had to get creative. They used spectroscopic and photometric distance estimates, basically looking really carefully at a star's light.
How does that work?
By analyzing its spectrum, the fingerprint of its light and its brightness in different color filters, you can make a pretty educated guess about what kind of star it is, and therefore, roughly how bright it should be intrinsically. Comparing that to how bright it appears, you can estimate its distance.
Sort of like guessing how far away a car is by the brightness of its headlights.
Kind of like that, yeah. It helped identify candidates for closer study, especially before the big multicolor all-sky surveys really kicked in over the last couple of decades.
Okay, so it sounds like piecing together a puzzle with fuzzy pieces. The paper then mentions some actual early attempts at catalogs. Tell me about those.
Yeah, some pioneering work. A really key one was by Richard Woolley, the British astronomer royal back then. He published his Catalogue of Stars within 25 parsecs of the sun in 1970, mostly based on those trigonometric parallaxes.
Okay.
And then there's the ongoing effort, the Catalogue of Nearby Stars, or CNS. That's been a huge project, mainly out of Heidelberg in Germany, running for over 60 years now.
And that CNS catalog evolved over time, right? It wasn't just one publication.
Exactly. It went through several versions. CNS-1 came out in 1950. It had about 915 single stars and multiple systems within 20 parsecs. But the distance measurements back then weren't super precise. Parallax errors were around 10 milliarcseconds.
Which is big or small?
Well, small in absolute terms, but large enough to introduce significant uncertainty for nearby stars. Then CNS-2 in 1969 expanded things a bit, reaching 22.5 parsecs, and refined the count within 20 parsecs to about 1049 stars.
Okay, getting better.
Then CNS-3 in 91 pushed out to 25 parsecs, listing around 1,700 stars. But the really big jump pre-Gaia was CNS-4 in 1997.
What was special about CNS-4?
It incorporated data from the Hipparcos satellite mission. That was a huge leap forward in space astrometry at the time. CNS-4 was pretty much the definitive list within 25 parsecs for a while.
So Hipparcos was a game changer then.
Oh, absolutely. A major step. But, and this is important, Hipparcos had a limitation.
What was it?
It could only observe stars that were already selected for its input catalog. It wasn't an all-sky survey in the sense of just looking everywhere. While it went pretty faint, maybe 11th or 12th magnitude, it was only really complete for stars brighter than about 9th magnitude.
Meaning it still missed a lot of the fainter, potentially nearby stars.
Precisely. Especially the M-dwarfs we talked about. Think of it like having a really good phone book, but only for people who registered beforehand. You miss a lot of folks.
Got it. And what about those other surveys mentioned? Recons and Superblank. Were they trying to fill those specific gaps?
Exactly right. They were targeting those overlooked faint stars. Recons, for instance, focused on finding red dwarfs in the southern hemisphere. Superblink used observations in different colors over time to pick out stars with high proper motion, which often flags nearby M-dwarfs that Hipparcos might have missed.
So let's sum up the pre-Gaia situation. What was our best guess for the local stellar population?
Okay, so before Gaia burst onto the scene, we knew of roughly 5,000 stellar systems within 25 parsecs. And a big northern hemisphere survey had found about 100,000 mid-dwarfs out to 100 parsecs.
Sounds like a lot, but I guess still incomplete.
Definitely incomplete, like having some detailed maps of a few city blocks, but no overview map of the whole city. We knew we were missing things.
And then, boom, Gaia. The cosmic census taker arrives. Tell me about this mission. Why is it such a revelation?
Right, Gaia. Launched in 2013, aiming for maybe a 10-year mission. Its job is basically to measure everything it sees in the sky, down to about 21st magnitude.
Which is incredibly faint, right?
Millions of times fainter than the naked eye can see. It's just staggering. And the key data release, Early Data Release 3, or EDR3, came out in December 2020.
Okay.
That covered the first 3 years or so. It listed positions and, crucially, parallaxes distances for nearly 2 billion stars. 2 billion.
Wow.
And the accuracy, typically better than 1 milliarcsecond, even for faint stars. A milliarsecond is like the angular size of a coin on the moon as seen from Earth. It's just phenomenal precision.
And that level of precision across billions of stars?
Yeah.
It's hard to wrap your head around. So what does this mean practically for mapping our immediate neighborhood?
It means almost any star brighter than 21st magnitude within 100 parsecs will be seen by Gaia, and its distance measured with incredible accuracy, usually better than 10%, often much better.
So no more guessing for most stars in that range.
Pretty much, and this led directly to the first Gaia catalog of nearby stars, the GCNS.
And the numbers in this new catalog, they're just off the charts compared to before.
Completely. This first GCNS lists 331,312 objects within 100 parsecs.
300,000. Compared
to maybe a few thousand known well within 25 parsecs before, and that incomplete 100,000 meter dwarf count out to 100 parsecs. It's easily a 100-fold increase in well-characterized stars in that volume, 100-fold.
That's astonishing.
And it goes deep. It includes stars down to spectral type M9, really cool, faint red dwarfs, only about a tenth the mass of our sun. It's like we suddenly switched from a blurry sketch map to a super high-res satellite image of our stellar neighborhood.
Okay, wow. Let's zoom right in. What about that very immediate 10-parsec bubble around us? What's the new head count there?
Right, within 10 parsecs, accounting for a few really bright stars that actually saturated Gaia's detectors, like Sirius, Vega, Procyon, the ones you can easily see.
The famous ones.
Yeah. Including those, we now know of 383 stars with really accurate distances in that 10 parsec sphere. That number includes 5 companion stars whose distances Gaia nailed for the first time.
Still some missing pieces, though.
A few caveats. That count doesn't include some known binary stars where the components are still too close for even Gaia to separate clearly. And there are almost certainly some super faint brown dwarfs, the T and Y types, that are just too dim even for Gaia, but it's vastly more complete than ever before.
So, okay, we have this incredible new census.
Yeah.
It's not just about counting stars, right?
Right.
What new insights are we getting about, say, the structure and dynamics of our local part of the galaxy?
This is where the really exciting science starts. With this amazing data set, we can pin down things like the sun's position relative to the exact midplane of the galactic disk much better. It's about 4 parsecs up, give or take.
Okay.
We can also characterize the thickness of the disk for different star populations. Older stars tend to wander a bit further from that midplane than younger ones, for example.
Interesting.
And the sheer number of velocities Gaia measures how fast stars are moving and in what direction it allows for incredibly detailed studies of the flow of stars, both individually and in groups, right here in our bit of the Milky Way.
And the paper mentioned tracing galactic orbits. How does that work?
Exactly. You take Gaia's precise position and velocity for a star now, and you use the laws of gravity and our models of the galaxy's mass distribution.
Right.
And you can essentially run the clock forwards or backwards in a computer simulation. See where the star came from, where it's going over millions, even a billion years.
And what does that show?
It confirms what we generally expected, but with amazing detail. Most stars in the disk, like our sun, follow pretty circular paths, staying close to the galactic plane. But those rarer halo stars passing through,
The tourists.
yeah, the tourists, they have much more stretched out, tilted orbits, plunging high above and below the disk. Gaia lets us see these different populations really clearly.
It paints a dynamic picture. What about our sun's own motion? Does Gaia refine that?
Yes, it does. We know the sun orbits the galactic center, of course, but it also does this little bobbing motion up and down through the disk's midplane.
Like a horse on a carousel.
Exactly like that. It oscillates up and down due to the gravity of all the stuff in the disk. Gaia helps nail down the period of that oscillation. It's roughly 80 million years for one up and down cycle.
80 million years.
And what's really fascinating, though still a bit speculative, is that some research has tried to link these passages through the dense midplane with, potentially, periods of colder climate on Earth, icehouse periods, over geological time.
Whoa, a cosmic connection to Earth's climate.
Potentially. The idea is maybe increased dust or gravitational effects during midplane crossings could influence things. It's an intriguing possibility, being explored thanks to data like Gaia's.
That's really thought-provoking. Okay, changing gears slightly. The paper talks about the luminosity function. What is that and why is it a big deal?
Right, the luminosity function. It's basically a stellar census, but broken down by intrinsic brightness. It tells you how many stars of a certain absolute magnitude or luminosity exist per cubic parsec. And you do this for different types, main sequence stars, giant stars, white dwarfs. It's crucial because it directly tests and informs our models of star formation and the whole star formation history of the Milky Way.
How so?
Well, if your model predicts, say, loads of faint red dwarfs should form, but the luminosity function shows fewer than expected, your model needs adjusting. Knowing the true distribution of star brightnesses is fundamental, and Gaia's nearby star catalog lets us map this function out with unprecedented detail and accuracy. It's like getting a super accurate demographic breakdown of our stellar city.
Understanding the stellar demographics.
Exactly.
Now, within this 100 parsec Gaia sample, the paper mentions a couple of familiar sites, open star clusters. The Hyades and Coma Berenices. Tell us about those.
Yeah, even within this relatively small 100 parsec volume, we find these two well-known clusters. The Hyades is probably the more famous one, visually.
That's the V-shape in Taurus, right, near Aldebaran.
That's the one. It's quite noticeable, a loose scattering of brighter stars. Gaia places it around 47 parsecs away, so about 150 light years. relatively close.
And Coma Berenices.
That's a bit fainter, subtler in the constellation Coma Berenices. It's further out about 86 parsecs, and people often think of the Pleiades, the Seven Sisters.
Very famous.
But that's actually just outside this 100 parsec limit, around 110 parsecs away. Still close, but not quite in the GCNS sample definition here.
And Gaia sees these clusters clearly.
Oh, absolutely. They stand out beautifully in the Gaia data, not just because the stars are physically closer together in space, forming a density enhancement, but also because all the member stars are moving through space together with very similar velocities. It's a dead giveaway that they form together and are traveling as a group, like a flock of birds.
And the Hyades in particular seems to be getting a lot of attention with Gaia data.
Yes, it's a prime target. Gaia sees around 500 definite Hyades members. And what's really cool is you can see the structure. There's the dense core, but also these two long, faint tidal tails stretching out.
Tidal tails, like pulled by gravity.
Exactly. Stars being slowly stripped away from the cluster's edges by the gravitational pull of the Milky Way itself, primarily the galactic center, over millions of years.
Wow.
And some studies using earlier Gaia data actually suggested something quite dramatic. The Hyades might be quite close to dissolving entirely, maybe only another 30 million years or so left as a coherent cluster.
30 million years. It sounds short for a star cluster.
It's blink and you miss it on cosmic time scales. Shows how dynamic the galaxy is.
Indeed. Are there other similar structures like streams or superclusters showing up in Gaia's view?
Yes, definitely. Beyond these nearby open clusters, Gaia is revealing all sorts of larger, more diffuse structures, stellar streams, moving groups, superclusters. Often these are the shredded remnants of older clusters or even dwarf galaxies that the Milky Way has swallowed.
It's galactic archaeology.
Kind of, yeah. You trace these streams by finding stars that share similar orbits and velocities, even if they're spread across the sky now. The paper mentions the Gaia Enceladus stream as a prominent example, thought to be left over from a major merger in our galaxy's past.
Fascinating stuff. Okay, what about binary stars? Two stars orbiting each other. How is Gaia helping there?
Binaries are super important, and Gaia is fantastic for them, especially for resolved binaries pairs where Gaia can actually see the two separate stars. Studies using the earlier data releases already found loads.
And the new GCNS.
The new GCNS sample within 100 parsecs clearly shows over 16,000 resolved binary systems. 16,000. And it seems about 10% of stars like our Sun, F, G, and K types are in these wide binary systems.
And why are wide binaries particularly interesting?
Because their gravitational hug is quite weak. The two stars are far apart, so they're not bound very tightly.
They seem fragile.
Exactly. They're sensitive to gravitational nudges from passing stars, giant molecular clouds, maybe even clumps of dark matter. So studying their orbits, how many there are, how wide they are, it tells us about the star formation process, but also about the dynamical evolution of the galaxy and the distribution of mass, including unseen mass. They're like delicate probes of the galactic environment.
Very cool. And finally, white dwarfs. The end state for stars like the Sun. What's Gaia telling us about them nearby?
White dwarfs really stand out in Gaia data because they're very hot but intrinsically quite faint. So when you plot their color against their absolute brightness, something Gaia measures superbly, they fall in a very distinct sequence on the diagram.
Easy to spot then.
Relatively easy to flag as candidates, yes. Based just on the Gaia photometry and astrometry, astronomers have identified over 20,000 high-probability white dwarf candidates within 100 parsecs.
20,000.
And the kicker is, more than 2,500 of those appear to be new discoveries, previously unknown white dwarfs right here in our backyard. It's massively expanding our census of these stellar remnants.
So, really, summing it all up, it feels like saying Gaia revolutionized our view of the solar neighborhood is almost an understatement.
It truly is. We've gone from a somewhat patchy, incomplete picture to this incredibly detailed, deep, and dynamic view. Hundreds of thousands of stars cataloged, their distances and motions measured with unbelievable precision. It's fundamentally changing our understanding of our local place in the Milky Way.
Just the sheer scale.
Yeah.
Hundreds of thousands of newly mapped neighbors. It's incredible.
Yeah.
So as we wrap up this deep dive, you're left thinking, with this fantastically detailed map now in hand, what else is hiding in plain sight? What further secrets about our galaxy's past, its future, maybe even our own solar system's journey through it all, are waiting to be unlocked in this data? Definitely gives you something to ponder.
Yeah.
Thanks for walking us through this cosmic neighborhood tour.
My pleasure. It's an exciting time for galactic astronomy.